Professor Zi-Kui. So before Professor Liu gave his talk, I can do a very brief introduction. I didn't get any introduction information, bio information from Dr. Liu because I know him very well personally. So I received a call from Dr. Liu like 21 years ago, and after that, I came to United States, joined his group, and then I officially started my career on CALPHAD. You know, before that, I have no idea. I even haven't heard about CALPHAD. So, but at that time, I didn't, realize that how CALPHAD will be, this kind of important thing in my life. So here, before Dorio gave his talk, I want to show my appreciation to him, bring me to this field. I'm proud to be a member of the CALPHAD community. All right, okay, so Dr. Liu, I gave you the right to share, so you should be able to start your talk.
All right, thank you for introduction. And I did have recording, so I'm going to press record, and then you can write your question. So where are you listening to the recording? You can type a question there, so I can answer question during the play of the recording. All right.
So I also opened here, so it doesn't matter, you share or I share, so both are fine.
Well, maybe it's better you share, then I can answer questions here too.
Okay, okay, that's fine.
Thank you.
So let me do that. Okay, so give me 1 minute. Where is my file? Oh, file is here. Okay, so share screen, share sound, optimize. So if you guys cannot hear, please let me know. I tried, it should work. All right, let's get started.
Hi, everyone. First, I want to thank the organizing committee for their efforts to organize this wonderful CALPHAD Global Conference. In this presentation, I'm going to talk about the next 50 years of CALPHAD. Where we all know predicting future is difficult, but let's see, based on what we have now, what the next 50 years may be or may look like. My name is Zi-Kui from Pennsylvania State University. And then last year, the National Academy of Engineering celebrated the 50th anniversary for one of their publications, The Bridge. Professor Sinod and I wrote an article for this special issue to discuss what will be next 50 years for the design of new materials. We all know that materials are closely related to human civilizations. And we talk about the prehistory of humanity. We had a Stone Age. The human used the natural materials. Then we had a human-made material, copper, tin alloys, which we call the Bronze Age. And after that, we had Iron Age. We used the human-made iron carbon alloys. And that made a big change of our civilization. Well, we call it industrial manufacturing materials 1.0 to 3.0. Concerns steam power, electricity, and computers. We all say now that we're in the industry 4.0, it's industry manufacturing materials 4.0. It is about digitization. So basically digitize everything. Well, digitization is about data. Well, it's more about knowledge. Right? We put our knowledge into digital form. And then let's look at manufacturing. We know that manufacturing is a process to form the products, use some material to serve one or two functions. And it's about changing materials, right? Liquid, solid, So top of it concerns phase stability. So what represents the phase stability or the knowledge of phase stability and functionality is thermodynamics. We know that in 1870, Gibbs established the combined law of thermodynamics. So it was until 100 years later that Kaufman proposed the CALPHAD to digitize thermodynamics. So thermodynamic knowledge becomes digital. And in another 50 years, we've been practicing CALPHAD, and like the presentation by Greg Olson and Jim Yoko, for the application, design materials. So what will be next 50 years for CALPHAD, or in general, for the knowledge, digitization of thermodynamic knowledge? Okay, let's look at what CALPHAD modeling is about. CALPHAD modeling concerns the Gibbs energy, modeling of Gibbs energy of individual phases as a function of temperature, pressure, composition, and even more importantly, is Kasai here. So Kasai represents the internal degree of freedom. Okay. So that means it's not only equilibrium, it could be non-equilibrium state. And we know that we use derivatives of Gibbs energy. There's quantities like heat capacity. We call them some chemical data, heat capacity, enthalpy, entropy, activity, and so forth, to derive the free energy function. In principle, there should be, those quantities can completely determine the free energy. However, the uncertainty of these free energy functions are large. So you cannot really predict the phase stability accurately, not in the accuracy we need for materials processing. So to improve those functions, then we need to use another set of data we call phase equilibrium data with phase stability, phase boundary, or tie lines, as Greg also mentioned in his talk, and also by J.C. Zhao. Basically at the equilibrium state, so there's no driving force for this process. So we'll get this process, then we start with pure elements. We make it to binary, to ternary, to multi-component system. So after we create this database, then we can do material design. Material design concerns equilibrium. Well, that's important. It also can use it also concerns driving force, right? For the driving for the precipitations. And in addition to, you can also do the physical chemical properties, which are secondary derivatives of Gibbs energy, or free energy in general. As you will see, that is beyond heat capacity, enthalpy, entropy. Is a wide range of properties we can predict for the derivatives of the free energy functions. Okay, so CALPHAD is about the models for the properties of individual phases. Well, we focus on the free energy function. And the CALPHAD is community. We have a website. We have a conference, annual conference started in 1973. We have a private foundation, CALPHAD Inc., since 1975. It supports the scholarships and awards for the community, and it supports conferences too. And we have a journal, CALPHAD Journal, since 1977. And to do CALPHAD modeling, of course, we need tools, and we created databases. And we have commercial tools. There's a special issue in CALPHAD, volume 26, issue 2. Had a number of papers on the software tools we have, including commercial ones, SummerCalc and FactStage, CompuSum with Pandat and GeoMat Pro and MetaCalc. And since that time, there have been some open source codes too. OpenCALPHAD, Thermochimica, and also HiCALPHAD SBay, which are developed in my group. And it has the capability to high throughput CALPHAD modeling with uncertain quantifications. Okay, I do want to mention that CALPHAD supports the ISME and MGI. And it is because of CALPHAD inspired me to coin the term material genome in 2002, and which is discussed in this paper I wrote in 2014. As Greg mentioned, in 2004, there was a publication on accelerating technology transition and discussed about the material genome concept, even though it didn't have the term at that time in that report, but inspired by the Human Genome Project. And also 2008 is a publication integrated computation materials engineering. In that report, it is stated, CALPHAD software is arguably the most important and perhaps the only generic tool available for ISME practitioners. That just is the importance of CALPHAD modeling. And then 2011 is Material Genome Initiative. Greg and Charlie Kuhlman wrote an article in 2014 on materials genomics from CALPHAD to flight. So CALPHAD has been very useful and for material design and for materials processing. As we know, as I mentioned, the CALPHAD model starts with pure elements, go to binary, ternary, and so forth. So it also gives us a challenge here. The challenge is that if we change the property of one component system, then we have to change all the properties, all the systems involve that element, all the binaries, all the ternaries. As you can see that for this 6-component system, and there's a lot of systems we have to redo, remodel, how to change the parameters. So that's very, very challenging and very, very difficult. And this is reflected by this chart, which it was in Richard Otis' PhD thesis. It basically it indicates that the one-way information flow. So we collect the data with the experimental DFT, and we translate them into the software format. And then during this transition, we lost a lot of information, metadata. And then when we get the data, we do the modeling. It's the iteration, okay, iterative process. So then we got the parameters. Now, when we got the parameters and all the history, and also the metadata lost, we got a database. So you can see a lot of information is lost during this process. So making it extremely difficult to remodel the system. Okay, so we have to think about this one, how to improve it. So we developed a PACAF and SBAY to do that work. And in 2018, I wrote a paper called Ocean of Data. So it really summarizes this kind of idea. Okay, the idea is that we need to integrate the first principle calculations, CALPHAD modeling with machine learning, and at the same time create an ecosystem for data. So when I talk about this idea, my idea with a communication staff in our college, she came up with this very nice diagram. Talk about the data ecosystem. Okay, so what it means is that we have a lot of data. Talk about data lake. We talk about the data stream. Okay, we talk about the company secret data, right? Proprietary data. But we, in principle, we should be able to collect all the data together, we'll connect them, and then we can use PACAF and SBAY to develop a databases, high throughput, and the database will into the cloud, and then they will be condensed again, right? Precipitation, and then go through this cycle. Okay, of course, they also go to the lakes, they go to the stream, and also go to the ocean. Then we should take this kind of cycle, a data ecosystem. So that's about ocean of data. So that's what I think is the future of CALPHAD. Talk about data application. So I wrote another paper last year about computation thermodynamics and its applications. Thermodynamics is way beyond the phase stability. Okay, Of course, it's very important. So I stability and metastability and instability. And actually those can be used to discuss across the phenomena. I'm going to hopefully have time for a few examples. Seebeck coefficient, Sorority coefficient, piezo ferroelectric properties. Okay. It concerns transport properties, diffusivity, conductivity, and even goes to mechanical properties like elastic properties or even plastic properties. Okay, now the question is really, as many people think, that is thermodynamics for equilibrium only. Well, if you look at it as a first law, no, it's not, because the first law never says whether the system should be equilibrium or not. However, if you look at the function by Gibbs in 1870s, that's for equilibrium, because the equation he had is du, which you know is TdS minus PdV plus summation of mu I dni. This is for equilibrium only. So what's different between these two is another term. Okay, it's entropy production. So if you add entropy production in this equation, then it becomes for non-equilibrium system. It's applicable to non-equilibrium system too. Okay. So now if the Gibbs energy or just switch variable, you see, now you have to add one more term. Okay, that's entropy production for internal processes. Okay, so that's what CALPHAD is about. So CALPHAD modeling is really for non-equilibrium systems, non-equilibrium thermodynamics. Okay, we can say that. Okay, the psi here is internal state variables. Like when we sublattice model, it's side fractions. Okay, side fractions. And in the afternoon today, June 24th, I will give a seminar called entropy. The title is entropy. Well, for the Duke University. Well, virtually. Now, if you're interested, you can sign up, and it's linked. Then in that presentation, I will talk about details, but the definition of entropy, how we use it, what its implications, what can we do more with it. Okay, now I mentioned that thermodynamics is not only about equilibrium, it's actually a lot of properties, not only heat capacity. Heat capacity is one of them. So we in the equation I showed before, we have X for the molar quantity, Y for the potentials. Now it's the derivative between these two, give a wide range of properties. Of course, heat capacity is here, okay? Elastic constants, permittivities, permeabilities, okay? They're all from the derivatives. It's the second derivative of energy. It's the first derivative between X and Y. So Y is here and X is there. So some expansion by the derivative, and all these coefficients are all in the derivatives of the free energy function. Now it's important here, the diagonal terms, they are always positive for stable system, for stable systems, but the off diagonal terms could be positive and negative, or zero, or infinite. Okay, of this diagonal can also be infinite too, but this could be negative or positive. Okay, so but the diagonal terms will always be positive for stable system. There's actually another type of new derivatives we have been discussing. I actually find it very interesting. Is the derivatives between the two potentials. For example, between the stress and the temperature. Okay. Or look at the last item, last row here, the chemical potential to temperature derivative. What's that? That's the thermal transport property. Because temperature driven chemical potential, driven diffusion, or driven electron migration, that's some electrical property. Okay. So you can see this this derivative, again, is a second derivative of energy, actually has a lot of properties, which sometimes people think is kinetic, they are kinetic properties, but it's actually some thermodynamic properties. Now, I do want to emphasize about this internal variable psi is very important. Okay. For example, when we do CALPHAD modeling, we talk about the non-stable lattice structure, BCC copper. Right? BCC copper, we need BCC copper is not stable, we know that. However, BCC copper can form in a BCC solution between iron and copper. Okay? So we need a free energy for the BCC solution, which needs the BCC copper free energy. And then BCC copper free energy, which depends on the FCC, and we call it lattice stability. So that's the foundation of CALPHAD modeling. And there's a lot of other internal variables like the mole fraction, side fraction, order disorder, and the polarizations, and the defects. Defects actually think about defects, they're actually internal degree of freedom, right? Dislocations, vacancies. Some of them are stable, some are less stable. Okay. The twins and the stacking faults and green bond, they exist there, right? They stay there. Okay. So those defects are very important if you want to talk about the properties. Mechanical property depends on dislocations, vacancies. So these internal variables are very, very important for us to understand materials. Okay, before maybe 20 years ago, the CALPHAD modeling is take experiment data and some estimations, put together, we do the modeling, we develop databases. 20 years ago, first principle calculations became available to us. But we know first principle calculation are most for zero degree Kelvin. Now you will put a statistical mechanics with the final temperature. Now you can see that we have experiment, we have first principle calculations, we get a statistic together, we can do a much better modeling. So it enhances the predictive power of database. As I mentioned, we have tools and database, so forth. Right now, database can be better. Of course, it also gives us a problem because now we're going to revise the database we had before, which we had 10 components or 20 components already, right? How can we revise the databases? Okay. So we need new tools. Okay. We need high throughput tools. Okay. We need uncertainty quantification for our predictions. Okay, so in my group, we have this a GitHub repository. All codes packages are open source. So they're divided into two groups of it. One, data generation. So I have machine learning code. We have DFT tool kit for French, for high throughput calculation. So you can go to download it. And then we have data processing. We got the data, then we do the use CALPHAD, can define new models, okay? And the SPA can do the parameter evaluation and with uncertainty, okay? And we also now created workshops, and the Material Genome Foundation is one of the nonprofit foundation we formed, and to promote this open source tools and for the community to adopt. And we do have in this YouTube channel, we have a number of recordings we had from previous workshops. Next week, Monday and Tuesday, we have another workshop for these tools. And the sign up sheet is available as the next slides or so. Okay, so now we got data generation, right? We got data processing. So we now want to create a data ecosystem. So we take the theoretical data, we take experiment data, we call them proto data. Okay, we call them proto data. That's machine learning, DFT, ab initio molecular dynamics, FEM, and experiment. And we use CALPHAD SPA to generate CALPHAD databases. Then you can do material design, and material processing, and the material service put in the applications. And in that process, we generate new data, right? The new data will fit into the proto data system, and then it goes through this cycle to improve the database. Okay. Of course, another thing is that when materials get used up, you can recycle it. The recycle will generate new data again. Okay, so now the idea is that because this ecosystem, the new data continues getting into the proto data system, and it continuously improves the CALPHAD databases, and then it continues for the new material design and the manufacturing, the service, and the recycle. Now, I once I show our DFTK is www.dftk.org. That's an open source high throughput DFT code to calculate the free energy. Okay, it builds up on the high throughput tools in the community, Pymagen, Fireworks, and the Custodium. This and Automate. They are used also for materials project. And then on top of that, we build this DFTK to do finite temperature and the finite and the variable compositions. Okay, because for CALPHAD modeling, we need temperature dependent, we need composition dependent. And DFT-based calculations are very good, very useful. However, it still takes time. So we want to make it more efficient. So you can take the DFT data, calculate data like, for example, the OQMD database or the materials project or other databases. When developer trains a new neural network, okay, they're going to make predictions, okay, make predictions. So there's one of the code we developed in the last 2 years called Superfund. As I showed on the website, you can download it from the website to use it. And you can see how good the machine learning models are with the database from the DFT databases and the predicted one. And you see the maximum absolute error is like 28 MeV. Okay, so it's in the accuracy of the DFT calculations. And also you can take your new data to do so-called transfer learning to improve the model. Like new data, which is not in the system. We're continuing to improve this tool. And now you got this big database, you get the machine learning models, you got a lot of structures. So we wanted to be able to put them together, okay? So we're going to calculate in machine learning, you have the data, algorithm, and descriptors, right? So we're going to calculate descriptors for all the structures. Like we created one called materials property descriptor database. So that means that in the future, when you get a new structure, it'll be much faster than now use machine learning model because the descriptor calculations takes the most of the time. So you can handle millions of structure very efficiently. And it's automatic processing of all available data. And the more important is that you can decentralize. It doesn't have to be do one computer, centralized computer. It can be different cloud resources. We're going to release this one very soon in the summer. You will be able to see it from our GitHub repository and also on our group website. Okay. Now you got all the data, right? So we want to speed up the development of the database and also use machine learning. Okay, so we develop a code called Aspect. It's high throughput modeling. Basically, evaluate the CALPHAD model parameters. We're doing the 2 steps. The first step is use the derivatives only. The French derivatives. As I mentioned before, the derivatives in principle can get a complete database, right, with all the parameters in the French function, basically do integration. Okay, but you have to make sure that you don't overfit. So it's a balance between number of parameters and the robustness of the model. So develop a algorithm for that. Now you get the initial set of data parameters now, right? So you can calculate phase diagram all the properties, but we know that the prediction of those models are not very accurate, particularly for phase stability. You could be 100 degrees off. So you need the second stage is use of phase equilibrium data and refine the model parameters. We use Markov chain Monte Carlo method and Bayesian parameter estimation. When you do the Bayesian parameter estimation, you get uncertainty quantification too. So in order to be able to do this kind of thing, we need a computing engine. Okay. And about 6 years ago, we started to develop the CALPHAD, which is was a PhD thesis of Richard Otis. It used advanced sampling algorithms to find the sampling, the starting point for calculations. And the very important thing of the CALPHAD is use symbolic computing in Python. You can develop new models. For example, we just recently implemented the quasi-chemical model into the CALPHAD. And in the future, it will be very easy for anybody to develop new models. So now let's think about this one, right? We not only the model for thermodynamics and also other property models too. And now remember that we talk about the internal degree of freedom, right? So you do equilibrium calculation, you minimize it, the internal degree of freedom is eliminated, they become dependent variables. So we have another function called calculate. So calculate is not for the minimization of energy, but for the given internal degree of freedom. So you can long equilibrium state, the energy of long equilibrium state. And Richard did great job for developing this code. And after graduation, he moved to JPL, NASA. And he continues to develop it. And then he put this software for competition for NASA Software of the Year in 2019, received a second place. So I have to think about this one, right? This is NASA-wide software competition, include all software engineers, okay, across NASA. And I really think Richard did a great job and to make this PyCalphad programming and demonstrated its impact to NASA. So as I mentioned, we had workshops. So we have next workshop on PyCalphad aspect. It will be next week. It's offered by Massachusetts General Foundation and Pennsylvania State University with support from IBM. IBM is going to provide the cloud computing for the workshops. And it will be complementary to the participants of the CALPHAD Global, this conference. And the registration website is here. Hope you take this advantage and to participate in the workshop. It will be around 2 days, Monday and Tuesday in the mornings in the Eastern US time. So now we put this together, right? We'll put the machine learning, we'll put our MPDD and the PyCalphad aspect together, we'll build this ocean of data. We call it CODA. Want to bring all data together. Okay, we can use cloud-based MongoDB database. Now it's hosted at the Penn State Virtual Machine. And we are going to develop a Optimate API. So Optimate API, Optimate is a new a kind of interface to connect the different databases. We find it very exciting. So we want to do that too. So people can access our data and our databases. And also tools too. Okay, so now we've got everything all together. Now what's next, right? So this as you can see, that it will not take us 50 years, right? Hopefully next 2 or 3 years, we have all the structure, all the infrastructure set up, and the database can be more efficiently developed, and can be efficiently updated with uncertainty quantifications. So now you can redesign new materials. Okay? So as Greg also mentioned before, talk about the design with CALPHAD. We call it, I think that's called a rational design with CALPHAD. The idea is that with the knowledge we have, and we kind of not guessing, but we get some ideas about the composition range. Then we do the calculations. Okay? We do design. Okay? And then we go through a circle. Okay, so it's called rational design. Is using human intuition or knowledge to change the input variables until the desired output is obtained. The question is, can we do better? Can we do it faster? Fewer iteration? And can we improve the even better materials, right? Get better materials. Okay. The idea would be, of course, as you would guess, is machine learning. Right? So we talk about machine learning, generate data and do the modeling. But can we use machine learning to do the design too? So actually it's possible. Well, at least under development. It's called the deeper generative learning. And we talk about the machine learning, people usually in the black box, right? Like a typical social science, right? There are no models. But we, as Greg also mentioned, we have physics, we understand it. So we really want to do physics-informed machine learning. We're called PIDL, PIDL models. And we are working with Professor Jintao Xu at the Department of Mathematics at Penn State. He has been doing machine learning for a long time. We are working on a project to take his expertise, apply it to materials. His physics-informed machine learning models. And then you get models, but it's still not enough, right? We need to do the inverse design. Okay. So it turned out the machine learning community, of course, is doing that too. So the one we're going to work on is called a conditional generative adversarial networks. It's called CGAN for inverse design. And our department had a new hire, Professor Wesley Reinhardt, and he's expert in that area. So we're working on that, working together, and on one project already from APAI to do inverse design of what, in this case, is refraction errors. Okay, I wanted to let you know that we do have recorded the presentations on this topic. And again, this presentation will be online. I know it's a PDF online too, so you can click it and watch those videos we had. Okay, this is just 1 or 2 slides about this called generative modeling. Of course, as you know, I'm not an expert at that one, but there are a lot of experts. For example, this book by David Foster, Generative Deep Learning. So it introduced the mathematics and include hands-on practice on this book. And nowadays we're into the Python programming, use Jupyter notebooks to run your calculations. Okay. There are a lot of publications recently, even after this book, and they just see how fast this field is moving. I will give a very simple, my understanding of this process is that it's really called latent spaces and the data abstraction. We know that the material's properties are determined by so many variables, right? So many variables. So it's impossible to look at all the variables, okay? But we can do the abstraction of these ones. Give you an example here is that, for example, look at this one, right? Look at this curved space here, right? Okay, but however, okay, if you flatten it, it actually becomes much simpler, right? Much simpler, okay? It's much simpler than before. And you think about this one in this space, these two are the nearest distance, but actually it's pretty far here in this space, okay? This space. So the latent spaces are low-dimensional representation of high-dimensional data. You can see, but this is high dimension, this is low dimension, right? So you want this one, so this can be represented. I just showed here 2D manifold from 3D space. Okay. You can see actually this three-dimensional space only has 2 dimensions, even though it looks like 3 dimension. Okay. The idea is that you flatten high-dimensional data, okay, to extract what to think of the meaningful features from raw data. So that process is a machine learning process. Okay, so just to give a little bit of understanding of my understanding of the neural network, right? Neural network actually is pretty simple functions. It uses a linear function, kind of linear transforms, and then there you have so that's what you get is functions here, okay? And then to the activation, okay? Another function is nonlinear, so I have linear and nonlinear, called activations. So Professor Xu gave me a lecture a few years back at one of the lunch we had together about this linear transforms and nonlinear activations. Okay. Now, if this looks very simple, right, for this one. However, if you put all of them together, okay, you put a lot of them together, so you can actually approximate any functions almost, okay? You can approximate all functions, okay? So the idea is really that you could put so many this kind of linear transformers and these activations together, they can basically mimic all kinds of functions. So why that works is because why it works and efficient, right? You have so many networks, so many nodes there, neural nodes, they're still very efficient because the linear transforms are very fast. Okay, nonlinear activation introduce complexity. Okay. And you put them together, stack them together, multi nodes and multi levels, you can basically reproduce anything. Now if we put physics into it, right? So we talk about specific networks for our properties, what we want. So that's what we're working on. So that's what I think would be next 50 years. And of course, it has been demonstrated that works, right? So I think the next many years, we're going to have is an inverse design workflow. Again, that's created by my colleague, Professor Ringhart. Okay, so for materials, right? For materials, we're going to train this neural network model and known composition and the property pairs, right? Knows composition, knows properties. Of course, in the middle, we're going to have something more in the middle, right? What do we have middle? Of course, we know the faces, right? It's property of the faces. Okay, so by pair this composition and property, and when we know the faces, then we can get the latent space of the connection. So basically, we have the conditional input and to neural network, and we get this latent space built up. Okay, and then we can specify each property, or isolate the fit one to optimize. Then we can propose the candidate materials based on the property we need. And in that case, we're including the computation screening first. We do the prediction, then we do the computation, just like the rational design, right? And then we do the down screening, the down selection from computational, and then do the synthesis. Okay, the idea would be that it would be much faster. It goes to the space which you may not have in there before. All right, so if you put it all together, that's the ocean of data. It's an ecosystem. As we know, that ecosystem never ends, right? It's an evolution process. You get new data, you get new property, you get new materials, then you get new data and new materials, new property, then you design new data, design new materials, right? This process never stops. Now we get better materials, more efficient to make the materials, and they have better properties. All right. With that, I want to thank you for your attention.
All right. Okay. That is great. So thank you, Dr. Liu, for your talk. So now I think we get into the Q&A session. For the audience, if you have questions, please type in this Q&A box, and we will promote you as a co-host, and then you can ask your questions. So you can ask questions to JC, or you can ask questions to Zi-Kui. All right, okay. So at first, let me see, JC, you are here, right? Oh, JC is not here. Oh, yeah.
Oh,
okay.
I'm here.
JC, yeah. Okay. All right. Let me see. We have some questions here. So the first one, let me promote first. Yeah, okay. So let me see. Natalie, promote to panelist. Okay, so make co-host. Make co-host. All right. Okay, so Natalie, you have questions, I believe, to JC, right? So you can share your camera, and then you can ask your question.
Yes, thank you for your talk, Jesse. The question I made during the talk was, first of all, for the parameters, binary determination of mobility, you had a table with before the number of parameters and what you got. Was that made with the same thermodynamic description?
Yeah, we have in the paper, we have the the direct comparisons for the using both so we have one set of data using thermocratic database thermodynamic description, another set of data using the literature, the same description of the literature data. Yeah.
It was the same thermodynamic description.
Yes, we have a set of data for the same thermodynamic description.
Thank you. Because this is something that some people are not aware. I mean, depending on the thermodynamic description you're using, of course, you will not get the same description of the thermodynamic factor, and then it will impact your final mobility. And the other question was, could you comment the effect on the diffusion of the magnetic ordering?
Yeah, so basically the magnetic ordering, when we use thermocratic to compute the thermodynamic factor, that's already included in there. That's why you see some of the wiggling around for some of the thermodynamic factor calculations. So that's already included in there. And but the effect is very small, except that we are very close to the Curie temperature or the Néel temperature for that particular composition, right? Away from those ones, the effect is very small. By the way, let me just comment on about your comments about thermodynamic factor is depend on the assessment. So we did this 18 binary system. I think about 10 of them, the thermocratic database generated the thermodynamic factor, and the literature one are exactly the same. And there are about 8 or 6 or 8 that are slightly different, and we provided the parameter for both set of data for those ones. Okay. So, and then the magnetic effect, as I mentioned, that's already computed in the thermodynamic calculation process using the thermocratic software.
But you are telling that experimentally also you don't see any effect on the magnetism on the diffusion?
It's very small. It's very small, unless you really go into the samples where most people are using are not fully like magnetically charged, right? They're just a natural state, right? You have a metal, you just use iron, and you use iron against nickel, and that's it, right? You did not fully charge the one with strong magnetic field to do that experiment. If you use that kind of experiment, yes, you have to consider that differently. But for lateral state doesn't have too much of an effect. Yeah.
Okay, thank you for your answer.
All right. Okay. Yeah. So thank you, Natalie. So the next one will be by Liang Yan, and after that will be Andres. So Andres, I will try to promote you to co-host while Liang Yan asks the question. So Liang Yan, please open your camera and ask your question. I believe this is to Dr. Liu.
Yes. Hi, Dr. Liu. This is Liang Yan from Dr. Wei Xiong's group. And thank you for your comprehensive presentation. And here I have two quick questions for you. And the first is, in some cases, the lattice stability calculated by DFT is quite different from what we have in the CALPHAD database. So what is your opinion about this difference? Do you think we should rely on purely the DFT calculated results because they are possibly more reliable or accurate? And the second is, I think a critical step in the thermodynamic assessment is to assign weight to these experimental data points. So for the SBA, can it automatically assign weights to the experimental data points, or we should still manually assign these weights?
Okay, thank you very much for the question. I think they are very important questions for us moving forward. And the first question about the light stability between the DFT and experiments. And it turned out that you don't just wrote a paper, submit to CALPHAD, talk about this issue and how we should do. I think that the question here is really the accuracy and the precision of the data. And we know that in the CALPHAD modeling, when Larry started the light stability, there were no very limited computational data from DFT at that time. So we did the light stability by extrapolations. Okay. So, and then DFT started to show the importance in maybe 30, 40 years ago. And then we find that it don't agree. Okay. And the issue, of course, now we know is because the instability. Okay, so extrapolation can never extract the instability. It can only extract the metastability. Okay. So that means that intrinsic disagreement. So that cannot be resolved, in my opinion. And you probably know that Axel did an approach. He said, okay, maybe we should use the instability limit. That's when the system becomes unstable. That's the limit, right? So the limit can be extrapolated by extrapolation, by CALPHAD method. That's why his agreement, his method agrees with CALPHAD modeling. That makes a lot of sense. Okay. Now, however, there's two issues here. One issue is that, as you the paper point out, that the instability itself is not the FC structure anymore. Not the structure anymore you have because structure changes, symmetry. Of course, Axel have different opinion on that. Okay. So from the accuracy point of view, the unstable state may not be bad for the energy point of view. But the unstable state cannot have entropy because it's unstable, right? So then we can use entropy fitting from the experiment data, high temperature data if you have, for example, top of titanium BCC, you have data high temperature. So you can use that data to refit back the entropy. Okay, so that means you get high temperature entropy, but again, we know at 0 Kelvin, entropy cannot be defined because it's unstable. However, it's stable at high temperature, so you can define entropy at high temperature. So that's why I kind of thinking that Yujon's idea, or Yujon's proposal to use the DF data exclusively may not be a bad approach. Okay. So I think we should try that. That's why I hope the PyCALPHAD expert tool can allow us to try it. Okay, that means we can do any light stability we want and see if it works or not, right? So that's why we developed the platform, so you can do that. But previously we cannot do it. Previously we could not do it because if you change that stability, you have to change everything. We could not do that, right? We don't have the infrastructure to do that. But I really hope is that the PyCALPHAD aspect will enable us to do more science. So in terms of two aspects, test different models, test different light stability. Okay. See which one works best for us, right? So that's science. Okay. So I think that's kind of the future. We can do science.
Okay.
The second question, what's the second question? I forgot the second question now.
Can S be
the
automatically?
Okay. Yeah. The error above the data, weight of the data. So currently, PyCALPHAD aspect give you a default weight of the data. However, we just have a new paper published with Richard was first author, is that we have a way now to gauge we're not called accuracy, but outliers of the input data. So we hope in the future version of the assay, based on that algorithm, it will give you suggestions what kind of weight you should use, or you say that set of data is terrible because it doesn't agree with the other data. Of course, it may mean that data is correct, right? Maybe the other data is correct. So it really depends on which one's right and which is wrong. It's not easy to say.
Oh, yeah.
So exactly, we hope we can give some judgment based on all that you have, and we do the sensitivity analysis to say, okay, this group of data does not agree with other data. Do you want to disregard them, or you want to reduce their weight? Right? So we can do that. So I think we have a mechanism to do that now, and we have not implemented it in SBA yet. But I think it's doable.
Yeah, I think that will be very important and speed up the thermodynamic assessment.
Yeah. So you give, of course, at the end, you can take default suggestion, or you can still override it, right? Because your human brain still knows better than the computer, so you can still override it. So you still have the mechanism to control it by yourself. But the computer gives you suggestions. I think that's very important. Computer programming will give you suggestions what may be good, but again, you still have to make the decision whether you want to take that suggestion or not.
Okay, I got your point. Thank you.
All right. Okay, that's great. Great discussion. So the next one will be from Andres to JC. So Andres, I want to confirm. So you said you don't have camera and mic. Do you don't have mic? If that is the case, I will read the questions for you. All right. Okay. So it looks like Andres don't have mic. So Jesse, the question is, which kind of analysis did you use to determine the concentration versus distance for the experiments where no nuclear tracers were available?
Yeah, right now, we are doing the order analysis we have been doing is using a microprobe, so electron probe microanalysis, so WDS analysis, using X-ray in the SEM, right? That's a very standard way of measure the concentration of metal so very accurate. The only problem there is the spatial resolution, okay? So it's about 1 micron spatial resolution for most of the time when we use a acceleration voltage about 15 to 20 keV. So when you have very steep concentration gradient, that's a problem. So we're trying to solve that problem now using other methodologies like an atom probe to measure the very steep gradient region, and then use the regular EPMA to do the composition analysis in the shallow region of the diffusion couple, because the atom probe is very expensive and you cannot do the whole concentration gradient by that. So that's what we do. I think the key thing is this forward simulation analysis allow us to get ready for all the uncertainties near the pure elements, because when the concentration gradient and the value of the concentration is very similar, is the automatic process of extracting diffusion coefficient has lots of problems. That's how the forward simulation solved that problem. Yeah.
All right. Okay. That's great. So the next one will be Shivani. I believe I promote you as a co-host. You have a question for Professor Liu, right? Go ahead.
Yeah. Okay. Thank you, Professor Liu, for the wonderful and inspiring talk. I'm really interested by the neural network that you mentioned in relation with CALPHAD. So can you elaborate on it, and how accurate will it be? Because it's to me it seems complicated. There are direct relations and so on. So what are your points on that?
Okay. Thank you very much, Shivani, for the question. As I mentioned that we use a lot of DFT data, right? Data from DFT calculations. It still takes time, takes a lot of effort to do this one, even though the high throughput we are simplifying. That the machine learning really kind of supplement to DFT data, so it can be produced much faster, but it most likely be less accurate than DFT compared to DFT calculated data. So the idea would be that you do more data from, you get more data from machine learning, but then you do a DFT kind of validation. And of course, DFT has to be validated by experiment too, right? So you get into sequence there. But we always know that DFT calculations are simplified, experiments are more complex. So we understand there will be discrepancies between that's one. So the idea would be that machine learning will be moving closer and closer to DFT-based calculations. Or even talk about the physical informed machine learning models. We hope we can even incorporate the DFT theory into the machine learning. So we actually approach that one, but because it's more efficient, so you can do more data. Okay, that's really the idea for the machine learning. So that could be that if you look at the S-Bay, this data will give you the first round of the parameter generation, because that's why it actually requires a lot of knowledge to do that part. That's actually the expertise, like Greg also mentioned, like Wei-Ming Huang. She has this kind of knowledge, Alida has this kind of knowledge, so they can jump this idea, these numbers for the brain and work on modeling. So it's very efficient. The idea would be machine learning can do more of that part.
So in case of exhaustive data, like a lot of data, it will be like more beneficial to use neural networks, I guess.
So my suggestion is that start with neural network and do DFT calculations.
Parallelly.
Parallel, or it will be, I think maybe DFT would be secondary.
Okay.
And then do experiments. Or if you cannot do experiments, work with Axel, Alex, and JC, got the data there.
Okay, so like all three together, and their overlap will be like a concrete system and validation with each other, and then we can say, okay. I understand. Thank you very much.
So basically, the space, machine learning does big space, and the DFT is smaller space, experiment even smaller space.
Yeah, so we are approaching top down.
Yeah, exactly.
All right. Okay.
Thank you very much.
Thank
Okay.
you.
That is great. So the next one is Daniel. I was trying to promote you as a co-host, but it looks like there's some glitch there. So in that case, let me ask Jesse one question. In your talk, you mainly talk about the research on the alloys, but at the end you talk about the conductivity investigation for ceramics. So can you talk a little bit more on that part? Because I personally am very interested in that, because we had publication on that by applying the CALPHAD approach to the perovskite conductivity predictions. So can you talk a little bit on that?
Yeah, I think the ceramic materials are a very important class of materials for many applications, right? And the point defect play a much bigger role in dictating the properties than in metals. And as you change the oxygen partial pressure and other conditions, they need to orders of magnitude of change of properties, and that's the Kruger-Wink diagram and the systematic description of those ones. I think I have a clear mind how we can establish the metals mobility database, atomic mobility database, very efficiently. But when you are dealing with the ceramic system, just getting so complex. Like, what is the pure elements or not pure element equivalent of mobility stability, right? But this, like the lattice mobilities and so on and so forth, and how much complication. And if we build a database on that in the future, how to establish that foundation, to basically the equivalent of the pure metal side of things, and so that we can move forward with this one. So I think there's some work that Jung Ogren did for the iron oxides, and there's some of those ones it looks quite good, but again, there's just so many parameters there. And then how do we reduce the number of parameters to the minimum so that we still have a very good description of the diffusion coefficient, and how to establish the foundation of the equivalent to the lattice mobilities for those systems. In my mind, I don't have a clear mind to say how to do that and how to do that most efficiently. I think, but the field, as a field, we need to figure it out and learn from what the Jung Ogren has done before, and see how we expand it into a more systematic framework for the oxides and other ceramic systems. That's my point. It's,
okay.
A lot of work, very impactful work, but it will take a lot.
Got it. So I will send you, my publication, and then hopefully we can pick up the discussion from there. All right. Okay, that is great. So the next one is Daniel. I hope that I pronounce your name correctly. I promote you as a co-host. I don't see you have a camera there, but can you talk?
I can talk. Thank you. Thank you. I have not a camera here, but I can talk.
All right, go ahead. Go ahead. The next one will be Wei Xiong. So yeah, that's probably will be the end of the our Q&A session. So Daniel, go ahead. Daniel?
Yes.
Yeah,
I have a question to Dr. Liu. What data, in your opinion, is more reliable? The ab initio data from DFT or other ab initio methods, or CALPHAD data from CALPHAD models optimized with solely with experimental data? Assuming that both DFT data and experimental data is robust and repeatable.
Okay, thank you, Daniel, for the question. As I mentioned a few minutes ago, is the accuracy and the precision. That's two different things, right, for the data-wise. So the CALPHAD data uses DFT data as input. Okay, so you cannot compare with which one is more accurate than another one. That's the first answer. The second answer about experiment data. Experiment measurements have two aspects. First is mostly measure the local equilibrium data, as Jason mentioned, local equilibrium. The second one is that it measures a lot of things together. It's combined things together. It's not just single event, single configuration, right? So that's complexity. But the FD data on the other side is more pure data. It's more well-defined configurations. And so it's very different compares to a lot of time. Okay. So I would think that the DFT data is like a portion of the experiment data put together. So it's really not a comparison to which one's right, which is wrong. It's rather that the experiment that includes some DFT data, DFT as input for CALPHAD modeling. Okay, so the experiment data and the DFT data together to make our CALPHAD database more valuable, more accurate to represent reality. So in my CALPHAD modeling chart, you see the one side is derivatives. That basically is about DFT data. Other side is phase equilibrium data. So we need to have both together to create a reliable CALPHAD databases. Either side is not good enough. For example, our early days of CALPHAD modeling is mostly from experiment data, phase equilibrium data. It works, right? But now we want to go beyond this. We want to make it more valuable, more accurate for the non-equilibrium state. Then we need to get more DFT data. So it's really a combination of these two give us the value of CALPHAD modeling. And so that's why CALPHAD modeling is beyond the experiment data, beyond the DFT data. It's the integration of them together to make us understand the materials better and the design materials.
Thank you very much for your answer. The actual question is, what weight should we give to the experimental data and for the DFT data?
It depends on where you get experiment data, right? If you get a JC school, you give it a very high weight. Okay. If you get the Professor Lavarsky school, you get a very high weight, right? So that's has personal judgment there. Okay. The data quality itself, that's one thing. And there's another thing is that you have no data, you have it based on DFT data, right? So it's really that the balance you have there is a balance there. But in general speaking, the experiment data is more accurate than the DFT data because the experiment capture more things than the DFT data.
It is also known that DFT relies on some approximations, such as generalized gradient approximation for exchange correlation energy. These approximations lead to intrinsic errors in the DFT data. The experimental data, on the other hand, can have errors related to probable to some
that's
unknown
exactly right.
reasons.
Yeah, that's exactly right. That's why you need to put them together, like JC mentioned, holistic approach. Okay, you need to put them together to understand the big picture. That's the key.
Are there any automatic?
So I think knowledge has the human input.
On the
human we have has to be part of the picture.
We cannot. So your opinion is that we cannot fully automate this decision process. What weight should we get to data?
Yeah, that's my question. The previous question. Let me answer the previous question. You can just automate it, give you some values, but they have to judge was that automation right or not.
Thank you.
Let me make a comment on this one. I think the difference between different states, if you compute it from DFT, that difference from FCC to BCC, and the relative difference is more accurate than the absolute value of that quantity. So sometimes you can take advantage of that to do the holistic integration. For example, if you have the FCC data very reliably, and then when you can compute that difference, and that difference you can add in there to be more useful than just the DFT absolute value alone. Okay, so that's one thing that I think it should be pointed out. The other thing is like the diffusion situation, the activation energy is more accurate. The prefactor D sub 0 is less accurate. So you try to leverage the accurate calculation part and then try to use experimental data to fit the other part. I mean, that's the kind of best scenario situation, what I call the holistic integration. And you take the advantage of both sides.
Thank you.
All right. Okay, that is great. So then let's get into our last question from Wei. He has questions for both Zi-Kui and the JC. So
yeah.
Wei.
Thank you very much. Both of your talk are related to the next 50 years. So I think education probably one of the most important part for the next 50 years. So I have one question to Zi-Kui. First one is, how do you see the change of the training related to CALPHAD assessment if all of this automatic assessment tool and computation tool becomes more and more powerful? Do you see the structure change? Second question to both of you is like, what experience can you share to engage more students, not only in the graduate student, but talking about general, like even the undergraduate student, because professor always directly interact with the undergraduate to learn the fundamental CALPHAD modeling and experiments. Thank you. Okay,
thanks for the question. Let me answer the first question first. And I think that the fundamentals will not change. So we need to teach people student fundamentals. We should emphasize thermodynamics is not for equilibrium, as people usually believe, and the CALPHAD demonstrates that it's not. Okay, that's a very important component we have to teach our community. So hopefully our students, whether they do CALPHAD modeling or not, when they graduate from university, they think thermodynamics is so powerful, covers the equilibrium and non-equilibrium systems. I said the first part. Okay, so without that part, it will be very difficult to educate people about CALPHAD modeling, so to speak. Now, to the CALPHAD modeling itself, and I think now we have a few good books published, so they give us the basics here, right? And as we have seen that in the last 50 years, we have different tools developed, right? So I think if we can give students solid foundations from their regular education, it will be much easier for them to adapt to new tools, for their interest to develop new tools too. So that means the training, in my opinion, the CALPHAD training aspects is really involved the tools development. Okay, so you get new tools. For example, I give training course for ThermoCAD from 1996 to 2011. Okay, so for more than 15 years, I gave to different groups in the United States most of the time. And now that's very good, right? So I covered some kind still doing that. That's important, right? But we have to move to the next stage, right? So that's why we develop new tools. And also, even more important, this training course we're going to have next week is actually can do this kind of completely cloud-based. So we're going to move to the cloud-based learning process. Okay, that's actually developing, right? Like the open courses, so many things is going on. Some people even say university will be gone in some years because it all will be free education online, right? But of course, we don't know that. But I think we have to go to this infrastructure, cloud-based learning process. Okay, so I move that one. But of course, you still have this basic fundamental understanding or to move to that stage. Okay, so there'll be some experts do the codes, tool development, make it easier. But we still have people to learn all the details to be able to do new programs, right? Because so it's a combination, I think. It's a combination of two together. I think that's my answer to your first question. Second question, let JC start first.
So the second question is about how to attract students, right? So when I was at Ohio State, we basically have like a third of our semesters as, we have computational, courses that are, a third of those one will be just using ThermoCAD and Dictra to do the calculation and the diffusion and precipitation, simulations. So those are the undergraduate students, the third-year undergraduate students. They start to get that kind of training, okay? Because Ohio State, there are a lot of metals, students interested in the metals field because Ohio State have a lot of faculty in that area. So at that time, that course was, it's still carried around. We use the developed modules for the, using ThermoCAD as the software to do that. And then on the graduate level, I teach basically a advanced course to teach a student how to use ThermoCAD and Dictra to do a lot of more, design and simulation and analysis of data. So that's a completely dedicated course for advanced training of Dictra and ThermoCAD. So that was very, very useful. And then I teach the fundamental core course for thermodynamics. And then you want to introduce a lot of those, lattice stability and all those basic concepts and the regular solution model and sub-regular solution model and how they can be used. I think the key thing is to link them to real phenomena like batteries and like how the thermodynamics drive diffusion, like what I was talking about, the thermodynamic factor. And if you do a regular solution model, you can really start to see that whether it's positive or whether it's greater than 1 or less than 1, just by look at the delta H, whether it's positive or negative. And so I think to get to the next step in the derivation so that they can relate those concepts together is very powerful, so that they know that all those information can be linked together and is related to their daily lives in terms of kinetics and everything like that. So I think that after I become a department chair at the Maryland, I haven't taught those courses yet. But Ohio State, they are continue teaching some of those courses.
Okay, I can add a couple comments on JC. JC is absolutely right. That's the education to our students. That's very important, whether they do CALPHAD or not in the future. So that we need that one, big base, right? Increase the base. So, and you just mentioned that before he joined my group, he had no idea about CALPHAD, never heard about it. Now he's one of the core CALPHAD practitioners, right? So that's going to it's important. He's Richard here, and he probably did not hear CALPHAD either. Now he's a package developer and with major force in the future, right? So that's kind of the same education. I want to give my own experience. Right? I as you know that the Packet Estimate is developing now. So last year, it's the first time myself used the Packet Estimate to teach my undergraduate class. So the student can go online and do the testing of the calculations, and they could do the homework too. Okay, so that we have to catch this kind of new technology in teaching. Okay, so students get excited. Oh, gee, you can do that, right? So they inspire them to get more involved. Of course, I want to thank Rich and Brandon. Brandon's here too. It's also my student developing aspect. So they put this kind of notebook together. So the new generations, they are accustomed to this kind of approaches, right? So we really should custom our teaching to them too. That's right. So I think we have to improve our teaching with the fundamentals of good application side. I think that's really important. Continue to develop new things, new tools, and new models. So excited students, make them see the future of their learning and for application side. I will add on that.
Yep.
Thank you.
All right.
The other
Okay.
thing, let me just one more comment. The other thing is really using practical examples, right? I mean, that's the most powerful. When you pull out a paper, and you ask the student, say, okay, go simulate this one without any other parameters. Just say, okay, this is the condition that they used, okay, for this particular thing. Just go ahead, you simulate. And when they did not put any parameter in there, and they simulated, they plotted the result is the same as the experiment, you see that that's the power of what the CALPHAD is about, right? And they get excited about that because, wow, I don't even need to do this kind of experiment. This experiments are completely unnecessary. I mean, that's the power, right? Yeah.
All right. Okay. Yeah. Thanks a lot for the thoughts of educations. I guess that's wrap up this Q&A session. Okay. So we still have 3 items left. So the next one will be official closing this CALPHAD Global 2021 by Professor Zi-Kui Liu. So Dr. Liu, you can share your screen of your slides.
Okay, I think you see my slides here.
Yeah.
And I am going to give a few slides about the closing remarks for this conference. And actually, those answer a question we should have about how to get young people involved. Let's see that. First, I want to thank the organizers, and they did a wonderful job to put this together. And this is purely initiated by the organizing committee, by Yu, Wei Xiong, Scott, and Richard. And they initiated, say, oh, we should have something, right? Because we didn't have it in 2020, we should do something. So it's not a regular conference because we could not travel, but I want to thank them for their efforts, extra efforts, because they're still going to organize the 2023 conferences, okay? So I want to really thank them for their efforts, for their willingness to support the community. As you have seen the poster session, it's fantastic. It's really fantastic with you see this video, right? Video and power presentation and so forth. It's really nice job. Thank you very much for all your work. And as you know that Marlin is going to say a few words about the 2022 Sweden and the 2023 Boston. As you see that we delayed everything by 2 years. So we haven't decided everything after that yet, but because some people could not delay, some organizers could delay. So we're trying to organize that one. Hopefully it will be updated on the website very soon. Again, let's go to this, I showed this slide in 1973, the first meeting in Boston. You see the young Larry Kaufman there, and you see the Bazir in the cloud playing table tennis, right? So I asked him for new photos. Do you have any new photos to show? Not everybody sent me, but I got to get one from Cloud. Cloud retired from Grenoble, and he has been playing Trump and in Austria there. Look at it. Look at his photo here. It's fantastic. Fantastic. Okay, so I want to show my experience because I know we have a lot of young people here. My first Catholic experience was in 1988. That was the excursion. As you know, CALPHAD meeting always have an excursion. That's when we had an excursion to a museum in Berkeley, 1988. And you see here is frame here. Frame was actually a bubble. You can blow the bubble and see how far you can blow before it breaks. So that's Larry and I were blowing together. So since 1988, I have attended 26 conferences, including this one. This one is not a regular conference, but it's also a meeting. And this is 1989, we had a conference in Sweden. As you can see, we about, I don't know how many people have here, but there should be quite a many people. Of course, you will see many familiar faces there. As John Arwin, Mats Hillett, Larry Kaufman, and Armando, now is Argentina. And Busuma is here. It's a developer of SummerCAD and Open CALPHAD. And if you do any physics, you probably remember Joran Greenbach. And so you can know a lot of people. So CALPHAD is like we say community, it's more like a big family because when you go to CALPHAD meetings, you stay together, the same hotel, you eat together for the whole week. Then we have only one session for the conference. So you stay all together for 1 week. And of course, the excursion was pretty interesting, right? So that's the time, 89, I was playing table tennis there. I found photos, Matsila, this is me. That's in 2019, in 1989, okay? Then we had an excursion again. And somebody took a photo when I was chatting with Larry Kaufman. That's 1989, gee, that's a long time ago. All right, so again, I miss this community. We have a conference and a foundation, we have a journal. And I want to mention this one, Larry Kaufman and Ima and Sarah, they wrote in 1973, talk about the importance of we get together, discuss our problems, and see how we solve them. And 1 year later, we come together again to discuss the progress we made and what the next steps we can take. Obviously, this meeting we are very, we say, oh, in the next 50 years, of course, it's going to change a lot, right? But we have some ideas, we continue to change our directions. It's really built up very lasting interactions and friendships, okay? Because you stay there for a week together, right? That's very unusual for any meetings. Okay, so now we have a lot of young people. Usually we get like 20-30% of people are young people for CALPHAD meeting. And many of them are first timer for the CALPHAD meeting, okay? So this photo was taken by Yu Zhong in 2003 in Canada. That's the first time you organize a young CALPHAD meeting. I don't know if Ying Ho is here or not. Ying Ho was a grad student at that time in Canada. So we all got together. And of course, Larry was there, and I was just starting to take over the journal editorship. So we talk about young people there, right? So I really want to welcome the young people to the CALPHAD community. Okay, I know that not all of you will continue doing CALPHAD modeling, but I hope you take the tool with you. Okay, it'll be one of the tools you can use in your future research. And as you know, we have a lot of awards too. We have a Kaufman, Chang STD scholarships every year. Now last year, we had the CALPHAD Young Leader Award. Okay, I hope you talk with your advisors and talk with your collaborators, ask them to nominate you. And we have Best Paper, Poster Award. This time we have 5 Best Poster Awards. And the TMS is another fund organization, also has a Kaufman Scholarship, which was established by CALPHAD Inc. And how does the future look like? It's very difficult, right? And during the Gazetton, I want to thank Wei Shun and the organizing committee to put the Gazetton together. It's fantastic. I got quite a few questions talking with young people. They were wondering what the future would be. But it's hard. Future is very difficult. That reminded me, I had a conversation with Wei Shun 20 years ago about when he was an undergrad student back in China, because he and I graduated from the same university, Central South University, so we had a lot of interactions there. And then I remember I had a very in-depth conversation with Scott, my comic, in 2018. That's when we met first time in Boulder, Colorado, at a conference there. We had a lot of interaction about that one. And I want to quote one sentence, one sentence which I learned from my dean at my college at Penn State. he said when he was a grad student, his advisor told him, when it is hard to imagine, imagine harder. And I put this one in one of my writing on one of the publications I had in the ISM magazine. So I do want to mention to young people, and when I started Penn State, I found that I have to constantly talk with my students and actually with myself too, because professor job is very, very challenging. And the success rates of proposals are very low, and it's become lower because it's become more competitive. So I thought I should kind of think, to put my thoughts together. So I developed a theory called the TKC theory. TKC stands for thermodynamics, kinetics, and crystallography, and I have a YouTube channel there. And I know that in China, people cannot access YouTube. So one of my former business students put on a Bilibili in China, kind of YouTube channel there too. And in this playlist, I want to mention one of the very interesting talk by Richard Otis, when he was asked to give a talk for emerging professionals at SM International. He put up a presentation, I think it's very interesting, called Do Impact Work. For young people, I really encourage to listen to his presentation. It's probably more connection with your thoughts, because Richard is a young person, right? Okay, I want to see you in the future CALPHAD conferences, and I want to see your manuscript submitted to the CALPHAD journal. I wish you all the best. Thank you.
All right. Okay. So thanks a lot, Dr. Liu. I guess that's pretty much wrapping up this CALPHAD Global. So then we need to think about the CALPHAD conference next year. So we have the organizer, Marlin here. Marlin, I think I promote you as a co-host.
I'm here.
Yeah. All right. Okay. So great to see you. So maybe you have some slides to talk about the plan for next year.
Yes, I will try to show my slides. Does that look okay?
Yes, this looks okay. Yes.
Yeah. Okay. So if you were in Singapore in 2019, you recognize some of these slides that I'm going to show. So hopefully we will have a CALPHAD meeting in May in Sweden. And we're actually not exactly sure where it will be, but we have two possibilities. And they are both very nice. And I'm organizing this conference together with the Thermocalc Software, Anders Engström, and I am from KTH in Stockholm. So the first one, or both, I show both here on the map. So one of them is situated in what you could think of as the middle of Sweden, in Dalarna, Tällberg. And that was where we were planning to have it, and we're not sure if it's going to be there or not. Or we will have it close to Stockholm in Lidingö. And that is actually where Mats Hillert lives. So it's close to his home. So if we go to Tällberg, it's a few hours on the train to get there directly from the airport, Arlanda. Or Lidingö is also easy to get to. So this is Tällberg in Dalarna. It's a nice place close to a lake, and very old fashioned, but nice, nice conference place. And this is the other one in Lidingö, also by the water. So both places are really nice. So we'll see which one it will be. And the topics will be, you will recognize them from earlier CALPHADs, and this was actually what we thought about 2019, but I guess they will be pretty much the same into 2022. So we go from experiments, ab initio, different kinds of modeling, both diffusion and thermodynamics, but also looking into other properties like thermophysical properties and ICME, and sustainability, and also what we have been discussing in the last few talks here, how it will be tomorrow. And here we were thinking of both models, methods, and tools, and maybe not for the next 50 years, but let's take the next 10 years maybe. So that was it. Since I don't know much more, then I just want to say that I hope we can see you all in Sweden in May next year. And I think it will be a completely physical meeting, no virtual meeting. But let's see what happens to the pandemic. So that was it, and you're all very welcome.
All right. Okay. That is great. Thank you, Marlene. So looks beautiful. So hope that we can control the pandemic well, and then we can physically go
This
there.
is actually my summer house, so that was just a picture I.
Oh, wow.
Yeah.
That's cool. That's cool. Okay.
But you're not coming there, all of you, so too many.
Yeah. Mm-hmm. Okay. That's great. That's great. All right. Okay. So at last, again, right? Thanks everyone for coming to this CALPHAD Global, right? So for this whole June, essentially. So yeah, we essentially get everything covered, except we still have this poster session held in Gather Town. So I just send everyone the link through chat there. So you can just follow the link, right? So I really encourage all of you go there. I believe you will have fun there. So so we will have the students there show their posters, and also I believe Zi-Kui or JC will also be there to answer more questions of their talks. So yeah, so that's pretty much it. Yeah, thank you everyone. All right, okay, thank you. So hopefully see everyone in